Hello. I do quite a bit of data analysis in a school of biosciences, and a lot of that is really trying to interpret the past. Because I think the mathematics I like to think is more like science fiction, because we use this to create the future. And I'll like to talk you through some of the more mathematical parts of the analysis of models, I suppose. Today we'll talk about state-space models and linear ones. So we can imagine a system such as this, the derivative of some state vector x, and that's linearly related to the vector itself x. There may be some inputs, some applied controls, and some observation function, which linearly depends on these states. And there's parameters involved. And of course, a lot of what we have to do as mathematicians is estimate parameters given some model structure and some data. And unfortunately, these structures are not always given adequate attention. I'm going to skip through a fair bit of detail, but basically this is the core of the problem, is that let's say we have our observations y for some interval of time, and we're looking for the alternative parameters theta prime, which is the alternative to theta, which can exactly reproduce that data. And depending on the number of solutions that comprise this set, we may or may not have a useful model at the end of it, which can be very frustrating if you find in this stoplight system that you're at the red light, which is a continuum of parameter space. The values are all equally good as far as your objective function is concerned. And then if you want to make predictions, different parameters give you very different predictions. So you're not able to make predictions with any confidence, and you may have wasted the time and resources in forming the model and collecting the data. It's also embarrassing. The orange light is that possibly you have a isolated solution, so that within any neighborhood of one of these potential theta primes, there's no other competing solution, in which case you may be able to deduce which is the true value, because you have information about the likely range of parameters. But what you'd really like is to be able to say from this, and this is an idealized inverse problem, so we're dealing with just the model equation. So it's a record of data that's infinite and error-free, and we assume that the model is the correct structure to represent the physical system. If you can get exactly one solution out of that, theta is exactly theta prime, then you don't need to make any discrimination between alternatives, and you at least can have some confidence that you're not wasting your time in collecting the data. You won't do as well once you look at a noisy, limited record of data, but at least you have a sort of a lower bound on the number of solutions you can expect to obtain. In practice, it's not so easy to work with equation one. So what we try to do is to say, let's try to find some features that summarize the output of our model structure, and that's these 5 vectors. So the system really becomes about solving where are these invariants, we call them, in terms of theta prime and theta, and the solution set is the same as that above, but we're not dealing with functional equations, we're dealing with algebraic equations. Just to give you a little bit of a flavor of that, reload. Is for a simple system, I started realizing that identifiability is pretty alien to a lot of people. So pictures are probably good, and maybe shiny apps are better. If we were to look at, say, a residual sum of squares here, we have some, assume that the model is correct and add some noise to it, then this sort of flat valley of despair here determines that maybe it's just the initial point of your search algorithm searching down the gradients is going to hit a point that may not be anywhere near your true parameter value. Maybe another illustration of this. For a simple chemical network is such as this, where there's rates of change, and that depends on a state vector of 2 variables, that we can easily find, if we do this analytical study, that if we were to change some parameters to some other parameters, we would be able to show exactly that the blue line and the red line are the same, even though the parameter values, the pair of parameter values are quite different from each other. And maybe you've seen this before, but it's surprising in other applications how this does seem quite foreign to a lot of people. Just recently, I was very fortunate to be at Matrix and with some disease modelers, and there was a papers come out in Epidemics, September Epidemics, and that got good reviews. And that had a section on identifiability in it, but I think it is still quite a novel thing. And so really the frontier is the communication side of this. So this is something that's very new, so I've started to think about how can you make the analysis side of it something that's going to be more comprehensible to maybe people who are not particularly mathematical, to make them aware of the importance of identifiability. So to quickly talk you through this is an interactive block of code in Maple, where I assume that I have, say, 3 states connected by some ordinary differential equation system, and I'm able to observe all of those states, and this is the output of solving for that equation 2, where I'm trying to find theta prime in terms of theta. And some of these parameters are free, so I'll never be able to estimate those uniquely, and some of the other ones I can estimate uniquely. And the idea is that people would be able to play with this and say, okay, if I was to say I cannot measure that observation X1 anymore, I've got a reduced system, and that changes. Now we have 2 distinct families of solutions for this. So this is very, very new work. I'm looking at sort of polishing this up in the near future. The ideas have been around, the basic ideas, probably since the 70s. The work that I'm doing is on switching systems, which have that abrupt change in behavior, as I showed on this diagram, where we have a certain phase and an abrupt change to another set of equations. It's surprisingly quite an unexplored problem, or not, because the usual tools don't apply. So there's some new mathematical developments to come out of that. So this has been the quick tour of identifiability and why you should care about it. And maybe the next time you're dealing with a non-mathematical collaborator and they say they just go on and use the models, they don't worry about it too much. You might say,
Spunk, are you out of your Vulcan mind?